Hi, good day, and welcome to my first video on electricity for the Physics CXC syllabus. Alright guys, now before we get started, I would like you to pause the video, get a ruler, a pen and a pencil, and I require you to take down these 7 formulas for me. These are formulas that are going to be introduced to you via examples throughout the video. Alright. So let's get started. Okay, electricity. Before we actually get into electricity, I just want to explain some terms that you're going to be hearing throughout. Now, I won't be able to explain all the terms as yet, just the basic terms. For the time being, we're going to be introduced to 3 terms: voltage, current, and resistance. I'm very sure that you're familiar with voltage and current. Now, resistance may be the odd one out. He's probably the one that you're not accustomed to. So let's start off with voltage and current. Voltage is measured in something called volts. And the symbol for volts is V. However, the symbol for voltage is also V. So voltage is measured in volts and the symbol is V. Current, the symbol for current is the letter I. Well, it's capital I. And current is measured in something called amperes. Now, a lot of people don't actually call it amperes. When you're measuring current, a lot of people just use the abbreviation and they just call it amps. The symbol for amps is just capital E. Resistance, right? Resistance is measured in something called ohms. The symbol for ohms is not the letter O, because you might think it's V, E, so common sense would say the symbol for ohms is O. It's actually this symbol here. That's the symbol for ohms. So now that we know each term and what they are measured in, I would like to explain the key difference between voltage and current. And when we understand these two, I would explain exactly what resistance is. So let's start with the easiest one. Current. Current is the flow of electrons. So on the board here, I have some electrons. Now, most of you all may know that, hey, electrons have a negative charge. So let's say we have a point A and a point B. Let's say this is the inside of a wire, inside of a copper wire. If the electrons begin to flow from the beginning of the wire, which I coined term A, and it tries to flow to the end of the wire, which I have coined term B, the flow of electrons actually moving from one point to a next point, we call it current. And this current, how much current we have, is measured in something called amperes, which most of the times I will call or abbreviate to amps. So the flow of the flow of electrons is current. So what is voltage? Well, tell me something. If I have a marker on this whiteboard and I want the marker to roll from point A all the way to point B, will the marker roll on its own? No. For it to roll or for it to move, you need to give it a force to push it forward. The same thing with electrons. If you want electrons to move from point A to point B, electrons cannot move on its own. You need to give it a force. That force, you can think of the force as voltage. So, voltage is the force that pushes electrons to give you a current. So that's the slight difference between voltage and current. Great. So, what is resistance? Well, I want you to think of resistance as the enemy of current. Resistance opposes current, or it tries to prevent current from flowing. So I'm going to mark a little definition here. Well, not a definition, just a simple explanation. Resistance, which is measured in ohms, is, well, he tries to oppose current. All right, here, tries to oppose current. Yeah, I spelled tries wrong here. Let me correct that. Sorry about that. Spelling isn't my strong point. So he tries to oppose current. Great. So he's like the enemy of current. So I'm going to put a diagram on the board now, and it would kind of relate voltage, current, and resistance to a real life situation. So give me a few seconds here. Let me look for this. All right. Now, this is a very popular analogy that you can find in a lot of textbooks. Here we have a water pump, a water system, and these are the pipelines. So you have one pipeline here, and when it reaches this junction, the pipeline splits into two. Then the two pipelines come together and they go back to the other side of the pump. The water pump, pushes the water. So I want you to think of the water pump as the voltage, and the actual water that is flowing, I want you to think of the actual water itself as current. So the water cannot flow on its own, just like electrons cannot flow on its own. You need something to push the water. You need something to push the electrons. So the water is the water pump is the force that pushes the water. Now here's the thing. Remember I told you that resistance is it's like the enemy of current. He tries to oppose current. So let's pretend we have a water line here, and water is flowing. So water is just flowing, and eventually it reaches this junction. We know in real life the water will split into two parts. Some will go below and some will go above. So let's assume that in this pipeline, the one on top, there's a little container. And I want you to think of resistance as gunk. Yep. Gunk. I'm not too sure if that's a real word, but I know a lot of people use the word. Gunk is going to be like stuff in the pipeline, like mud and deposits. It's basically things that you don't want in your pipeline. Now, look at this. The one above has more gunk than the one below. This one has a lot of filth in it. From a realistic point of a realistic perspective, if this one has only a little bit of gunk and this one has plenty gunk, which one will allow more water to flow? Well, the one above will have much more water, so I'm putting more arrows. This one here is blocked up more, so it will have less water. So I put more arrows here to indicate more water is flowing here and less water is flowing here. Resistance is the gunk in the pipeline that opposes current. And this diagram actually makes sense, because you're going to find that if there's plenty resistance, like in this case here, plenty gunk, there will be less current. If there's only a little bit of gunk, in other words, a low resistance, there will be more water or more current. So the point I'm trying to make here is this. Resistance and current are like opposites. Whenever your resistance is low, your current will be high. And anytime your resistance is high, your current will be low. The reason I am telling you this is that whenever you're doing calculations, you want your calculations to make sense. So anytime you see a low resistance, expect your current to be high. And anytime you see a high resistance, expect your current to be low. And I'm going to be pushing that in your head over and over and over when we do calculations. So every once in a while, I'm going to bring back this diagram. Also, if you have water flowing here, let's just say we had 5 liters of water flowing. So hope you all can see the 5 properly here. So 5 liters of water flow through here. Remember, water is like current. So the water flows here. So 5 liters reaches this junction. Some will go above and some will go below. So let's say that over here has a lower resistance, so more water will go above. So I'm thinking 4 liters would go above. So how much would be left to go underneath? Well, it would be 1 liter. Even though this one has more water or more current, and this one has less water or less current, eventually the water has to recombine at this junction and flow through. How much water do you think you will have here? Well, the 4 plus the 1 will give us back the 5 liters. So if you have, remember, current is measured in amps. So if I have 5 amps at the beginning of a junction, when the current, it doesn't matter if more goes above or more goes below, when the current meets back at the end by the other junction, the total current has to be, the output current has to be equal to the input current. And I'm also going to be reminding you of that fact over and over. Right. So what we're going to discuss now, before I actually show you how to calculate voltage and how to calculate current, we are going to actually learn to calculate the values of resistance first. Most teachers will show you how to calculate resistance first and afterwards show you how to calculate current and voltage. Well, from my experience anyway. All right. So now we're going to be calculating the value of resistances. Okay, well, I want you to pause the video and I want you to take down these 2 formulas for series and for parallel. And don't worry, I will explain what series and parallel means. Okay, so I'm going to put back this paper here. It's going to come back into view when we need it. So like I said, we're going to be calculating resistances now. Now remember, resistance is measured in something called ohms. And the symbol for ohms is that funny looking symbol there. Now, there is a circuit symbol for a resistor. Now, there are actually 2 circuit symbols for a resistor. A resistor can be represented by a squiggly line or a rectangle. Both of them are acceptable in the exams. Usually when I draw my diagrams, I use the squiggly line because for me, that's way easier to draw for some strange reason rather than the rectangle. All right, so there are 2 configurations you can arrange, 2 main configurations, you can arrange your resistance. There's one called series and there's one called parallel. Let's do the series first. It's the easiest one we can come across. In a series setup, I have 3 resistances. Now you don't have to have 3, you can have 2. But in series, the resistances are hooked up one after the other. So the squiggly line is like the resistor, and these are 2 wires coming out the resistor. And this wire connects to this resistor, and this one connects to this one to form a line. Whenever you want to find the total resistance in series, let's go back to this formula here, RT stands for total resistance. And to find the total resistance, you just add all the resistances. Now on the formula sheet, I have R1 plus R2 plus R3. Obviously, if there was a 4th one and a 5th one, it would just be R1 plus R2 plus R3 plus R4 plus R5. It goes on and on. So what's the total resistance of this? Well, it's really simple. To find the total resistance in a series, you just add up all the resistances. This is the easiest possible thing you can get. 3 plus 5 is 8. 8 plus 10 is 18. And resistance is measured in ohms. Really simple. Now, I just want to tell you what the total resistance actually means. Instead of buying 3 resistances, 1, 2, 3, you can throw away these 3 resistances and replace it with 1 resistor with 18 ohms. This and this would basically have the same effect in the circuit. So let's try a next one here. This is a slight trick question. Here we have how much resistances? 1, 2, 3, and 4. Now, don't let the little bend get to you. If I take this wire and just push it upwards like this, if I just push it upwards like this, it would form a straight line. So it would still be a series. So you can consider this to be a series because it forms basically a continuous line. The line is not straight, but a continuous path. I think that's a better word. Now there's a slight trick here. This one is 600 ohms, this one is 40 ohms, but this one is 2K ohms. K stands for kilo, and kilo just means they need to multiply it by 1,000 first. So 2K ohms is really 2,000 ohms. 2 multiplied by 1,000. And I tried to trick you here also. I put 0.06 kilo ohms. So we have to multiply this by 1,000 first. So when we multiply this by 1,000, we will get 60 ohms. It will move 1, 2, 3 places. So this here is a series. So to find the total resistance, we just need to add up all the resistances. So let's do this. I probably need my calculator here. 600 plus 40 plus 2,000 plus 60. I believe the total resistance RT is 2,700 ohms. So that means I can throw away these 4 resistances and replace it with 1 resistor of value 2,700 ohms. So series is probably the easiest configuration to deal with. Let's deal with parallel now. Now parallel is different. In series, the wire forms a continuous path. But in parallel, the wire splits into different portions. It can split into 2. In this case here, the one below, it splits into 3. 1, 2, and 3. So in parallel, there's a split. So I just wanted to show you the difference between series and parallel in terms of how the wires are arranged before I actually erased it. To calculate the total resistance in parallel, it's a little bit more difficult. You just can't add the 3 and the 6. In fact, let me put back the formula in front of you here. Right? I'll keep it here. In parallel, you have to take each resistor and throw it underneath 1. The 1 is understood. That's part of the formula. And the resistor, if it's only 2 resistors, we only do up to here. And we have to add them up. And then we have to apply this -1. What does the -1 mean? The -1 means inverse. So that means when we work out the brackets, whatever we get, we have to flip it. So I'm actually going to do it for you now. If I want to find the total resistance here, so it's this one I'm working on. To find the total resistance, I have to take each resistor and throw it underneath a 1. So I put 1 on 3 plus 1 on 6. And I'm going to add this up. So I'm going to use my little primary school addition skills. The LCM is 6. 3 into 6 is 2. 2 by 1 is 2. 6 into 6 is 1. 6 by 1 is 1. So we are going to end up with 3 on 6. When we add it up, whatever we get, we have to flip it. So we have to flip this answer. When we flip it, we will get 6 on 3. And of course, 3 into 3 is 1, 3 into 6 is 2. So the total resistance is 2 ohms. So you all understand that? When you add it up, whatever you get, when you throw it underneath 1 and add it up, whatever you get, you have to make sure and flip it. Great. So what does that mean? It means that the total resistance is 2 ohms, which means these two resistances, I can throw them away and replace it with one resistor of equivalent value, 2 ohms. And it should have the same effect on the circuit. Right? So that's what total resistance does now. It gives you an idea of, it allows you to throw away a lot of resistors and replace it with just one resistor. That's how I want you to think of it. Let's do a harder one here. Let's find the total resistance of this parallel configuration. So there are 3 resistors in parallel, 1, 2, and 3. And you know it's parallel because when the wire comes here, it splits 1, 2, and 3. So let's find the total resistance. To find the total resistance, we say 1 on R1. Well, 1 on 10 plus 1 on 5 plus 1 on 8. So we're going to add this up. So we need to find the LCM. I believe the LCM is 40. 10 into 40 is 4. 4 by 1 is 4. 5 into 40 is 8. 8 by 1 is 8. 8 into 40 is 5. 5 by 1 is 5. Let's add this up. 8 plus 4 is 12. 12 plus 5 is 17. Okay? So we're going to get 17 divided by 40. Right? Let's double check in my answer. Right. When we add this up now, please don't forget to apply the last step. We have to inverse our answer or flip our answer. So when we flip it, we get 40 divided by 17. It's perfectly okay to represent this as a decimal. So 40 divided by 17 will give me 2.35 approximately. I rounded off the answer, sorry, to 2.35. That means I can throw away these 3 resistances and replace it with one resistor with value 2.35 ohms. This concept of throwing away a lot of resistors and replacing it with one resistor should be very familiar to you, This concept is also present in something called resultant forces, which was section E, or one of the first topics you would have done in Form 1 or Form 2. A resultant force is when they give you a lot of forces and you simplify it just to get one force. Remember, forces in the same direction you add, forces in the opposite directions you minus. So it's almost a similar concept in this case. So we know how to do series, we know how to do parallel. So what would happen, if they combine series with parallel? So I'm going to do a question with series and parallel. Right, so here we have a circuit with a mixture of series and parallel. The parallel should be very easy to identify. This here is the parallel, right? So here's how you find the total resistance here. I would suggest that you find the total resistance of the parallel section first. So let's concentrate on this section. Alright guys, now when you're working out this question, work it with me. Just don't watch me do it on the screen. So let's figure out what we can replace these 2 resistances with. So how do we find parallel resistance? 1 on R1, so it's 1 on 6 plus 1 on 10. And when we add this, we have to remember to flip it. So the LCM here is clearly, well, it's actually 30. 6 into 30 is 5. 5 by 1 is 5 plus 10 into 30 is 3. 3 by 1 is 3. So we will get 8 on 30. but we have to remember to flip our answer or to inverse our answer. So let's inverse that. So, well, when we inverse it, it's really 30 divided by 8. So let me type that in our calculator. 30 divided by 8 is approximately, well, it's actually exactly 3.75 ohms. So what does that mean? It means that these two resistances, you could imagine it disappearing, and you can replace it with just one resistor. And the value of that one resistor is 3.75 ohms. But look how simple it is now. When you throw away those two resistances and replace it with one, this one resistor is now in series with the first resistor. And how do you find the total resistance in series? You just add the two of them. So the total resistance of the entire circuit is 5 plus 3.75, which is 8.75 ohms. Let's try another one. All right, so here's the new question, and I want you to find, we're going to find, the total resistance. It only looks scary. Believe me, it's going to be super, super easy. First of all, we have a mixture of series, and in between, we have two parallel configurations. When you see them stacked up on top of each other, or if the wire splits into different pieces, you know it's parallel. So how do we find the total resistance? Well, I think we should figure out the parallels first. So let's concentrate on this guy first. Forget him, forget him, forget him. Let's concentrate over here. So, how do we find the total resistance in parallel? In parallel, we take whatever resistances we have and we throw it underneath a 1. So it's 1 on 1 plus 1 on 2 plus 1 on 5. The LCM here, I believe, is 10. 1 into 10 is 10. 10 by 1 is 10. 2 into 10 is 5. 5 by 1 is 5. 5 into 10 is 2. 2 by 1 is 2. So when we add this up, we are going to get 17 on 10. Don't forget to flip it, because in parallel, we have to flip it or inverse it. So when we inverse 17 on 10, we get 10 on 17. Top goes on underneath, and the underneath goes on top. Let's reduce this to a decimal. 10 divided by 17 is roughly 0.59 ohms, because resistance is measured in ohms. So what does that mean? When we add up these three resistances, which are in parallel, we get a total resistance of, we get a different color here. Those three resistances can be replaced with one resistance of value 0.59 ohms. We're going to do the same thing over here. These two are also in parallel. So it's 1 on 6 plus 1 on 3. LCM is 6. 6 into 6 is 1. 1 by 1 is 1. Plus 3 into 6 is 2. 2 by 1 is 2. So we will get 3 on 6. And don't forget, we have to inverse or flip our answer. So we will get 6 on 3, and we know 6 on 3 is 2. 6 divided by 3 is 2, and it's ohms. What does this mean? It means we can erase these two resistances which are in parallel and replace it with one of equivalent value, 2 ohms. Look how simple this is now. This is no longer parallel and series. This is only what now? Series. All the resistances form a continuous part. So how do you find the resistance in a continuous part or series? You just add them up. So let's add them up. 11 plus 0.59 plus 2 plus 20. And we get a total resistance of 33.59 ohms, which means we could throw away all 4 now and replace it with one resistor of this value. All right. So now we are going to do some actual calculations that involve not only resistance, but current and voltage. All right, now there's a lot of formulas in front of you here. You're not going to concentrate on all at the moment. For the time being, you're only going to concentrate on two things. One, the golden rule of circuit calculations, and this guy here. You don't care about the rest of these. So in case you can't remember how to use the triangle, anytime you're trying to find current, which is represented by the letter I, and current is measured in amps, you block the I. So how do you calculate current? Current is just voltage divided by resistance. If I ask you to calculate the resistance, you can block the R and you're left with voltage divided by current. And if I ask you to calculate voltage, well, you can block the V and you will be left with current multiplied by resistance. Very, very simple. Now let me explain what we're going to be doing in this particular question. There are three resistances here. 1, 2, 3. And all three are connected to a cell or a battery. I know most of you all are not accustomed with the word cell. Just think of a cell as a battery. A battery has a positive terminal and a negative terminal. The long side is called the positive side of the battery. The short line here is the negative. Conventional current, I'm just going to call it current for the time being, but notice I use the word called conventional current, which I will explain later on. Current flows from positive all the way to negative. So this is like the water pump. Let me pull out this diagram here. Right, remember this old diagram? Right. The battery is like the water pump. It pushes out water, better known as current, and the current will flow through the resistances. Okay, so here's the thing. In any circuit calculation, no matter what, once you see the resistances are connected to a battery, I want you to find the total resistance and the total current, no matter what. I advise you to do this whether or not the examiner tells you to do it. You do it. So first, we always find the total resistance. So this is a series calculation. Well, so far there are three resistances. And how do you find the total resistance in series again? You just add them up. So let's add them up. R1 plus R2 plus R3. 6 plus 12 is 18. 18 plus 2 is 20 ohms. So the total resistance is 20 ohms. So we did that. Now we have to find the total current. What do I mean by the total current? The total current is always the current coming out of the battery, just outside the positive terminal. So I'm going to put IT here for total current. So how do you calculate total current? It's very, very simple. To find total current, well, first of all, we're going to use this formula. Current is voltage divided by resistance. If you are trying to find the total current, you need the total voltage and you have to divide it by the total resistance, which we have here. So let me put this working over here. To calculate the total current, when we block the I, we need the total voltage divided by the total resistance. The total voltage is the voltage of the battery. Remember, voltage is measured in volts. The total voltage of the entire circuit is 220. And remember, we found the total resistance, which happens to be 20. 220 divided by 20 is 11 amps, because current is measured in amps. So how much current is coming out of this battery? It will be 11A or 11 amps. Great. I'm going to erase this word here. Okay, so we follow the golden rule. Always find RT and IT. Now here's how series has a rule I need you to follow. I'm going to make a note of it. In series, all the resistances have the same current. In other words, if 11 amps flows out into the 6 ohms, 11 amps will flow out, and that same 11 amps will flow into the 12 and out of the 12 and into the 2 and out of the 2. So series has what? Resistance has the same current. So that's a rule I want you to add in. And that's going to be very, very important. There's something else I need to add here. But anyway, let's move forward. You have 11 amps flowing into this resistor. So the current here is also 11 amps. The same 11 amps that flows into here will come out of this resistor and also flow into this resistance. And the same current that flows out of the 12 will flow into the 2. Right? So in series, all the resistances experience the same current. So we calculated the current for each resistor. Now I want to calculate the voltage for each individual resistor. To calculate voltage, we need to block the V. V is current by resistance. So if you want to calculate the voltage over here, you have to zoom in over here and only take values from this area. So to calculate voltage, we need the current in this area and multiply by the resistance in this area. So let's get my calculator here. The voltage. Voltage is current multiplied by resistance. In this area here, the current is 11. And how much is the resistance? The resistance in this region is 6. So my total voltage is 11 multiplied by 6, which obviously is 66 volts. If I want to calculate the voltage here, I need to zoom in on this region. In this region, to calculate the voltage, I have to take current over here and multiply by the resistance. So let's do that. Should be pretty easy. Current in this region is 11. Multiply. How much is the resistance in this region? 12. 11 by 12 is 132 volts. So the voltage over here is 132 volts. So how do we calculate the voltage here? We have to zoom into this area now. To calculate the voltage over here, we take the current here, which is 11, and multiply it by the resistance, which is 2. 11 by 2 is 22 volts. Great. Now, just to get the terminology correct, you always say current flows through, but the voltage does be across. Okay? The voltage across this resistor is 66. The voltage across this resistor is 132. And the voltage across this 2 ohms is 22. But the current flowing through each resistor is 11. Now you will notice something. In series, when you add up all the voltages, 66 plus 132 plus 22. When you add up back all these voltages, we get back the original amount from the battery, which is 220, which is a good way to double check your calculations are correct. Now, in a series, let's just summarize. In a series, the current through each resistor is the same, but do not expect the voltages to be the same. The voltages are usually different, right? So resistance has the same current in series, but voltage may be different. Right? The only way all the voltages would be the same exact value is if the actual value of the resistances were equal. But here's 6 ohms, here's 12 ohms, and here's 2 ohms. So do not expect the voltages to be the same. If here was 6, and here was 6, and here was 6 ohms, then the voltage would be the same. Alright, so that's how you calculate current and voltage for a series configuration. So remember, take this note down. In series, all the resistances has the same current, but the voltage across each one may be different. So I'm going to do a parallel calculation for you now. Alright, so here we have a parallel configuration, and 2 resistors are in parallel, the 8 and the 24, and they're both connected to a battery. Now, just like the previous question, the long side is positive and the short side is negative. Current will attempt to flow out the positive side, go around the circuit, and come back to the negative side. So for this question, for each resistor, we're going to try to calculate the current and the voltage. Now, I know this is a parallel configuration because if you follow the line here, when it reaches here, the line splits. Some goes here and some goes here. Remember, the battery is like the pump and it's pushing water out. So it's pushing water out, and when it reaches this junction, some of the water will go this way and some of the water will go above. So there's a split in the pipeline. But before we move forward, the golden rule is what? No matter what, we have to find the total resistance and the total current. So this is a parallel configuration. So to find the total resistance, we take each resistor and we throw it underneath a 1. 1 divided by 8 plus 1 divided by 24. And when we get our answer, we have to flip it. So it's only 2 in parallel today. The LCM will definitely be 24. Over here you will get 3. Over here you will get 1. So we'll get 4 on 24, and we have to flip it or inverse it. When we inverse it, we will get 24 divided by 4. 24 divided by 4 is 6 ohms. So that means the total resistance of everything in the circuit is 6 ohms. Right? I'm going to have to erase this, so make sure and take it down. So the total resistance is equal to 6 ohms. Step 1 is complete of the golden rule. Next, we are going to find the total current. To find the total current, we have to take the total voltage and divide it by the total resistance. How much is the total voltage? The voltage of the battery, which is 72, divided by the total resistance, which we have now, which is 6. So 72 divided by 6 should give me 12 amps. So coming out of this battery, the total current flowing out, I'm going to put IT, is 12 amps. So you can think of it as 12 liters of water flowing out. And when the 12 liters of water reach this junction, some is going to be flowing upwards and some is going to be flowing this way. Now, you're going to realize to a point, series and parallel are opposites. Let's go through some basic, a trip down memory lane for a little bit. In series, the resistance, each resistance has the same current, but voltage may be different, but that's for series. In parallel, this is what you can expect. In parallel, the current through the resistance, all these notes here are for the resistances. The current will be different. In series, the current is the same, so they are opposites. Voltage may be different for series, but in parallel, the voltage is usually the same. And I'm going to introduce something called a photocopy. You'll understand what a photocopy is. It has to do with the voltage being the same. So I'm going to leave this here because these rules here are for parallel. What do I mean by the voltage is the same and this photocopy in brackets? What's the voltage of the battery? You notice this resistor, and this battery are in parallel. They're stacked up on top of each other. In parallel, the voltages are the same. Now, let me explain what not to do. I'm going to do something a lot of students do. They see the voltage as 72 volts, that's the total voltage, and they see two resistances. So they say 72 divided by 2 is 36. So they think he gets 36 volts and he gets 36 volts, making the voltage the same. And if they had 3 resistances, that's a total if, they would take the 72 and divide it by 3, and one person will get 24 volts, one resistor will get a next 24, and the other resistor will get a 24, making the voltage the same. And they think they are following the rules. But that is not what happens. It is true in parallel, all the voltages are the same, but everybody takes all the resistances, take a photocopy of the voltage. So let me draw this in. What's the total voltage? 72. He will take a photocopy of the voltage. So the voltage across this resistor is 72, and the total voltage across this resistor will also be 72. The voltages are the same, and each resistor took a photocopy of the voltage. All right, so that is what this note means. Okay, we calculated, we reasoned out the voltage for each resistor, so this is complete. Let's calculate the current through each resistor. To calculate current, we have to take the voltage and divide it by the resistance. So if you want to calculate the current here through this resistor, you need to take values from here going through this particular resistor. So I'm going to get my calculator here. To calculate the current over here, we have to take the voltage over here and divide it by the resistance over here. So the voltage in this region is 72 divided by the resistance, which is 8. And we will get 9 amps. So the water flowing through here, or the current flowing through this resistor, is 9 amps. So current is, I'm going to call it I1. I1 is 9 amps. Let's try to find the current through this particular resistor. So to calculate the current through this resistor, we have to take the voltage here, which is 72, and divide it by the resistance here, which is 74. So let's do that. 72 divided by 72 divided by 24. I get 3 amps. So this current here, which I'm going to call I2, I'm going to put 3 amps. I hope that's visible. All right. So for each resistor, we have the voltage. The voltage here is 72, here is 72, and the current, we have it for each resistor. Here's 9 amps, here's 3 amps. Let's see if our answer makes sense. Remember I told you current is like a water line, like water going through a water line. If I have 12 liters of water and it reaches a junction, some will go up and some will go so, right? Now, more goes up and more goes to the left, to the right. But when you add back the 9 and the 3 liters, you are supposed to get back the original amount. And 9 plus 3, if you backtrack, will give you back the 12. So that's one way of double checking your answer. Here's another way that I know that I am most likely right. Let's bring back an old diagram. Remember I told you from the beginning that resistance is the enemy of current. Whenever you have a low resistance, you can expect a higher current because resistance is like gunk. The less gunk you have, the more water or current can flow through. The more gunk you have, in other words, the higher resistance, less water can pass through because it's merely constricted. Let's see if that happened in our question. Well, over here, we had 8 ohms and here was 24 ohms. So the resistance over here was higher. The resistance here was lower. So that means over here has more gunk. You notice the current here is less. Less water can flow through this resistor. Where the resistance was lower, it had less gunk. So more water or current could flow through the top. So that's another way of trying to reason out if you're on the right track. It has to actually make sense. So let's do a question now with both series and resistance, series and parallel in the same question. Right, here's the next question. Here we have a mixture of parallel and series. These two are the parallel, and of course this one here is the series. Now when you're working a series and a parallel, it's a little bit more working you have to do, obviously. However, we still use the golden rule. Now I might need the space on top here, so I'm just erasing this, but just know that for each resistor we will be calculating current, voltage, and well, we have the resistances already. So let's follow the golden rule no matter what. Let's find the total resistance. Let's find the total resistance of the parallel first. So for parallel, as you all remember, parallel is, we're finding the total resistance is 1 on 3 plus the 1 on 6. And when we add these two, we have to flip it. So the LCM is 6. So we get 2 plus 1 here. We will get 3 on 6. If we flip it, we get 6 on 3, which by now you all know it's 2 ohms. So here's how you can visualize it. You can pretend that you throw away these two resistances and replace it with just one resistance, and this one resistance has a value of 2 ohms. This 2 ohms is now in series with the 18. So how do you find the total series resistances? You just have to add them. So that means the total resistance is just 18 plus 2, which is 20. So the total resistance, RT, is just simply 20 ohms. That's the total resistance. Next, we have to find the total current. To find the total current, well, let's pull the formulas. So formulas here. To find the total current, we have to take the total voltage and divide it by the total resistance, which we now have. So let's do this. By now, this should be pretty simple. So I'm not going to write down all the working. Just going to get my calculator here. The total voltage is the voltage coming out of the battery, which is 440. So we're going to take 440, I'll put my calculator on, 440 divided by the total resistance, which we now know is 20. So the total current is 22 amps. All right, so let's draw something onto this diagram now. Remember, I told you that this is like the water pump. So that means coming out of the battery, we have 22 amps or 22 liters of water. The water is going to begin to flow. I'm not too sure if I mentioned this. Current always tries to flow from the positive side, go all the way around the circuit and come back to the negative. So that means the water will flow eventually. Well, I should draw it down here. Let me draw it down here. It will flow and flow and flow. Eventually, it will reach this junction. Some will go upwards, some will go downwards. For the time being, we don't know how much of the 22 liters go above and how much of the 22 liters go below. All we know is that when the water recombines eventually, the current or the water at this junction here will also be 22 amps. And that current will flow back to the negative side. Alright, so I hope you can visualize this. The water is flowing, it splits into two parts, and it recombines here to come back to the negative terminal. So, anytime you have a mixture of series and parallel, I always tell students, hey, always pay attention to the series first. Right? I'm erasing this 2 amps. Remember, this was just for imagining purposes to show that this resistance is in series with the 18. Let's do the series calculation first, the series resistance. Now, I want to make this very clear. I am not doing the series first because the series comes first. That has nothing to do with it. I am doing the series first because it's proper procedure to do the series first. If this 18 was here after the parallel, if the series was after the parallel, I would still do the 18 first. Series first, parallel calculations after. Well, that's when we're calculating current and voltage. So here's what we do now. Over here, we know the current at this point is 22 amps. 22 amps is flowing through this resistor. Let's calculate the voltage across this resistor. To calculate the voltage over here, we need to take what? The current over here and multiply by the resistance over here. So, to calculate the voltage is current, which is 22, multiplied by 18, which is, well, that's a big number. Yes, now let me double check that. 22 multiplied by 18 is 396 volts. So that means the voltage here is 396. Now let me explain why I always like to do the series first. I like to always call the parallel, his nickname is Scraps. So parallel, his nickname is Scraps. Let me explain what I mean by scraps. The scraps has to deal with voltage. How much voltage did we push into this circuit? Into this circuit, we have 440 volts. How much did the series eat? He ate 396 of the volts. So if we take the 440 and minus the 396, we are left with just 44 volts. So 440 was pumped into the circuit. The series, the 18 ohms, ate 396, which means only 44 was left. What is left is called the scraps, the scrap voltage. Guess who gets thrown the scraps? The series eats like a king, and whatever is left, he throws to the peasants. So, remember I told you that in parallel, the current is different, but the voltage is the same. And everybody in parallel takes a photocopy of the voltage. So this is how it will look now. 44 is thrown to the peasant parallel circuit, resistors. 44 volts. Do not take the 44 and divide it by 2 amongst the 2 resistors. Don't say 44 divided by 2 is 22 and put 22 volts here and 22 volts. They all take a photocopy of the voltage. So that means the voltage here is 44 volts and the voltage here is 44 volts. So the voltage here is that and the voltage here is that. Everybody takes a photocopy of the same voltage. Now that we have the voltage and the resistance, we can figure out the current here. If we want to figure out the current here, we have to take the voltage here and divide it by the resistance here. So let's calculate the current over here. Well, the same current flowing through here is the same current coming out here. I don't have any space here, so let's calculate the current here. Current is voltage 44 divided by the resistance, which is 6. And we will get 7.33 amps. So let's calculate the current above. To calculate the current above, we just need to take the voltage here and divide it by the resistance here. So current is voltage, which is 44, divided by the resistance, which is 14.6666. So if we round it off, it's 14.67 amps. Now let's see if this actually makes sense. Let's make sense of our answer. Remember, we had 22 liters of water flowing in here. Some went to the top and some went to the underneath. How much liters went to the top? 14.67, and underneath 7.33. Let's add it back up. 14.67 plus the 7.33 gives me back the 22 liters of water, or the 22 amps. So I know my calculation is most likely correct because it makes sense. What about from the resistance point of view? Whenever you have a low resistance, the current is supposed to be higher, and whenever you have a high resistance, the amount of water flowing through is supposed to be less. Let's see if that makes sense. Well, here's 6 and here's 3. Here has the higher resistance and here has the lower resistance. The higher resistance only has the lower current. Look, 6 ohms and 7.33 amps. Where the resistance is lower, where it has less gunk, more water flows through. Lower resistance, higher current. So I know most likely I am correct in this question because everything adds up and everything makes sense. All right, so let's try our next question. In this question today, I really want to utilize the rest of the formulas on this sheet. It's going to be really, really easy. All you have to remember is anytime that you're trying to find something, you just have to block the relevant items. And whatever you're left with, well, that's the formula to find the item. But don't worry, I'll be taking you step by step through this question. So before we even get into the types of questions that I'm going to ask you, in almost any electrical question, let's follow the golden rule. Let's find the total resistance and the total current. So let's get started. Let's find the total resistance. Well, these two resistances are in parallel. So let's find their resistance. It'll be 1 on 5 plus 1 on 15. The LCM here, I believe, is 15. 5 into 5 is 1. Sorry, 5 into 15 is 3. 3 by 1 is 3. 15 into 15 is 1. 1 by 1 is 1. So here we have 4 on 15. And remember, whenever it's parallel, what do we need to do? We need to flip the answer or find the inverse. So it's really 15 on 4. So 15 divided by 4 is equal to 3.75, and resistance is measured in ohms. Okay, the resistance of the parallel configuration alone is 3.75. Remember, try to imagine this, that you throw away these two resistors and you put one resistor in its place. And this one resistor has a value of 3.75. So the 3.75 is in series with the 1.25. And whenever you're finding the resistance of a series, you just simply add. Okay? So I'm just pulling back the formulas here just in case you forgot. Series, you just simply add. So all we have to do is take the 3.75 and add it to 1.25, which would be pretty simple. 3.75 plus 1.25 is 5. So that means my total resistance, RT, is just simply 5 ohms. That's the resistance of the entire circuit. All right, so we have RT. Let's find IT. To find the total current, it's really simple. To find the total current, we need to take the total voltage, which I believe it's 200 volts. That's the voltage of the battery. So it's 200 divided by the total resistance, which is 5. So let's do that. It's 200 total voltage divided by the total resistance, which is 5. Well, 200 divided by 5 is 50. What? No, sorry. It's 200 divided by 5, which is 40. So the total current coming out of the battery is 40 amps. So let me write that in here. This is the total current coming out of the battery. Total current is 40 amps. All right. Now, that 40 amps is like water. It's going to flow until it reaches this junction. When it reaches this junction, it's going to split into 2 pieces. No one said it was going to be 2 equal pieces, but it's going to split into 2 pieces either way. And when it recombines here, you will get back the original 40 amps, which you can think like water, as water. So you can think of it as 40 liters coming back together. All right, so let's draw. Let's see how this is going to go. I'm still going to draw it out like water flowing. Water is just flowing. When it reaches here, piece is going to go on top, and some of the water is going to go underneath. Okay, we will get to the parallel current last. What I want to do is figure out the voltage across the 1.25 ohms. And when we get that, the remaining voltage or the scraps will be thrown to the parallel. So the current is going to come back together here. When it comes back together, the current over here, I should have drawn it a little bit smaller. The total current flowing through here is 40 amps. So it should be really easy to find the voltage across this resistor. To find the voltage across this resistor, all we need is the current through this resistor, which we have, and multiply by the value of this particular resistance. So, shouldn't be too hard. Let's try this. To calculate the voltage, let me clear some space here, guys. Sorry. I came really unprepared today. I just have an extra hour today, so I'm really trying to squeeze this in. Let me move this. Alright, so let's try it here. To calculate the voltage here, voltage is current multiplied by resistance. So let's take the current, which is 40, and multiply it by the resistance, which is 1.25. When we do that, the voltage across this resistor is 50 volts. Great. Now, let's look at this. If the total voltage is 200 volts, and the series eats up or takes 50 of those volts, how much would be remaining? It's just 200 minus the 50. Which leaves us with 150 volts. This is the scrap voltage. This scrap voltage will be thrown to the parallel configuration. And remember, in parallel, everybody takes a photocopy of the voltage. So that means the 150, this resistor will experience 150 volts. And this resistor will take a photocopy and will experience 150 volts. So I was going to put V is equal to that and V is equal to that. Although the volts should have given it away that this is a voltage. Alright, so let's do some current calculations now. I should be able to predict which one would have the higher current. Over here is the smaller resistance and over here is the larger resistance. So the smaller resistance is supposed to have a higher current, and the larger resistance is supposed to have a smaller current. So let's see if we end up with a situation like that. Remember how you calculate current? Current is just voltage divided by resistance. So to calculate the current here, well, okay, let's probably use this arrow here. I is, sorry, 1 second, let me just fix this up so it looks a little bit better. All right, current is voltage divided by resistance. The voltage is 150 divided by the resistance over here is 5. And I get 30 amps. So over here is just 30 amps. Let's calculate the current here. To calculate the current here, we need to take the voltage here, which is also 150, and divided by the resistance here, divided by 50. And my answer for this part here is 10 amps. And my answer actually makes sense. Look at it. The smaller resistance has a current of 30, and the bigger resistance has a smaller current of 10 amps. So my circuit calculations are making sense. So most likely, I am on the right track. All right, but this calculation here is no stranger to the previous question. I just wanted to point out that when we were following the current, the parallel configuration came first and the series configuration came after. But it didn't matter to me. I still calculated the voltage across the series first, even though it came second. And then I threw the scrap voltage to the parallel configuration. Remember, when we're doing, after we find RT and IT, if you have a mixture of parallel and series, always do the series first after this step. After this step, no matter what, handle the series first. Okay? So, let's try the harder formulas now. Well, not the harder formulas, the other formulas. Let's say, let's clean up this here a little bit. Let's say I wanted you to calculate, let's try these 3 formulas here, right? If I wanted you to calculate the power at this resistor, at this particular resistor. So let's try that. Power. I want the power at this resistor. Forget about the other resistors as yet. The nice thing about power, anytime you're calculating power, power is measured in watts. There are 3 formulas to calculate power. Power to me is the easiest calculation to get correct in an exam because you have 3 formulas and anyone will give you the same answer, and I'm going to prove that to you today. Let's start off with this formula. If I use this formula to calculate power, power is current multiplied by voltage. So let's try that. To calculate the power here, we need the current here. The current is 30 and we multiply by the voltage. So it's 30 multiplied by 150. And I get 4,500 watts. But let's say somebody didn't want to use this formula. Let's say somebody wanted to use this formula to calculate power. Well, to calculate power using this particular formula, you have to take the current, square it, and multiply by the resistance. So let's try that. Power is I squared multiplied by R. The current over here is 30, so it's 30 squared, and the resistance is 5. So let's try that on our calculator. 30 squared multiplied by 5. And we still get back the 4,500. Let's try this formula and see if we would get the same answer. To calculate the power using this formula, we block the P. Power is voltage squared divided by resistance. So power is voltage squared divided by resistance. Well, how much is the voltage over here? It's 150 squared divided by the resistance, which is 5. Let's try it out. 150 squared divided by 5 is 4,500. Great. So let's try another formula to calculate something else. let's say they wanted you to calculate the, let's use this resistor. Let's say they wanted you to calculate the amount of work or energy at this resistor. So they want you to find work or energy. Work and energy is the same thing. So to calculate work or energy, work is what? If we block the W, work is Q multiplied by V. Q stands for charge. Now the thing about it, we don't have the charge. At this resistor, we have the voltage. What's the voltage at this resistor? The voltage at this resistor is 50, but we do not have the charge. So we need to figure out the charge. So we have to go to our next formula. We can probably use this formula. To calculate charge, we just have to take the current and multiply it by the time. This question would be impossible to do without additional information. Let me show you why. To calculate the charge, we have to take the current and multiply by the time. Nowhere in this question has the time. But usually in the exam, if you read the question carefully, somewhere in the question, they will tell you how long the circuit was on. So let's say I didn't notice that, so I went back to read my question, and somewhere in the question, they told me the circuit was left on for a time of 3 minutes. Okay? So, knowing this now, I can calculate the charge. So, charge is current multiplied by time, but the time has to be in seconds. So this is a common trick in the exam. 3 minutes is the same thing. We are going to multiply by 60, obviously, to convert it to seconds. 3 multiplied by 60 is 180 seconds. So now I can calculate my charge. Charge is current multiplied by time. So at this resistor, my current is 40 and my time is 180 seconds. That gives me a charge of 7,200. Well, charge is measured in something called coulombs. Okay, right. So if I had to calculate work, I needed to take the charge and multiply by the voltage. But I did not have the charge, so I used another formula to get the charge. And when I finally got the charge, I replaced it in this formula. So let's finish off the question. Work is charge multiplied by 50. Well, charge multiplied by voltage. So the charge is 7,200. We're going to multiply it by 50, and we get 360 with 3 zeros. Yes, I'm seeing correct. 360,000, and work or energy is measured in joules. Okay. All right. So what else can we calculate from this? Well, we have charge, we could get current. Well, let's try to calculate at this resistor. Let's try to calculate the power. All right. Let's see if we can actually do that. Actually, no, we have the power. We don't need to use this formula to calculate the power. Power is just I squared R. That should be really easy. If we wanted the power at this resistor, we can choose any one of these three formulas. If we chose this one, power would be current squared multiplied by resistance. So the current here would be 10. So we would say 10 squared multiplied by the resistance, which is 15. So 10 squared multiplied by 15, our power would have been 1,500 watts. All right. Now these formulas are really, really easy to use. Whichever one the examiner asks you to use, you just block it. And whatever you are left with, that's the formula. And sometimes you may need to combine two formulas. Like in this question where I did not have the charge, we were trying to calculate the work. So I had to go to a next formula, calculate the charge, and bring it back to this formula. It's pretty common in most exams. All right, so next question coming up. All right, so welcome to my next question. This question is a mixture of two topics on the syllabus. It's not only electricity, but I'm also going to bring something called specific heat capacity that will have done that normally most schools do before. That falls under the heating section in your physics syllabus. Anyway, it doesn't matter if you didn't do it or not. I'm going to explain it from scratch in any case. All right. So let's say we have water. So we have a container of water. Let's say the water is at 25 degrees Celsius. If we want to get this water to be hotter, let's say we want to raise it from 25 degrees Celsius and we want to drink some coffee, so we want the water hotter. Let's say we want the temperature to be around 76 degrees Celsius. That's the temperature we like our coffee. Obviously, if you have water and you want to heat it up and make the temperature rise, you have to give it energy. By giving it energy, you can raise the temperature of the water. So let's try to find out how much energy we need to give this water in order to raise it from 25 degrees Celsius to 76 degrees Celsius. And let's assume it's let's say it's 0.08 kilograms of water, right? I'm assuming that's I don't know how much that is, but let's assume it's this amount of water. So let's calculate how much energy we need to give this 0.08 kilograms of water to raise it from 25 degrees Celsius to 76 degrees Celsius. On the syllabus, there is actually a formula that you can use to calculate this energy. And the energy, the formula says to calculate the amount of energy, heat energy, to give it. All we need to do is take the mass of the water, we need to make sure it's in kilograms, multiplied by something called the specific heat capacity of the water, which I will get to very soon. And then you have to multiply it not by the temperature, but the change in temperature. Change in temperature is completely different to just plain old temperature. And I will get to that just now. So let's use the formula. To calculate the amount of heat energy required for this particular situation, we need the mass of the water. It has to be in kilograms. Well, I gave you the mass of the water in kilograms, it's 0.08. The specific heat capacity of water, it's a value that you need to learn off. Just like how you learn off that the approximate value of gravity is 10 meters per second squared. The specific heat capacity of water, or the approximate value, is 4,200, and specific heat capacity is measured in something called joules per kilogram degrees Celsius. Remember, if you didn't do this entire topic as yet, don't rack your brain too much right now. Just know that the specific heat capacity of water is 4,200. Different substances have different values of specific heat capacity. Water is 4,200. I believe iron, let's say you're trying to raise the temperature of iron, I believe iron is just 320. Don't quote me on it, but it's roughly, I believe that is how much. So different substances, water, iron, even salt water will have a different specific heat capacity. The water I'm talking about here is plain, purified water. So to find the energy, we just take the specific heat capacity of water, which is 4,200. And how much is the change in temperature? Well, we started off at 25 degrees Celsius and we are raising it to 76 degrees. So the change in temperature, we have to minus these two. 76 minus 25 is 51 degrees Celsius. Note that your change in temperature can be in degrees Celsius or it could be in Kelvin. It doesn't really matter. If you notice that the entire screen got darker, it's because well, a storm is headed this way, and I'm not lying, a storm is actually headed this way, and if the clouds just actually covered a lot of the sunshine. So I actually use natural lighting for these videos. So that's the reason the video is looking darker. So let's calculate the amount of energy we need here. 0.08 multiplied by 4,200 multiplied by the change in temperature, 51. So that means the energy is 17136, and energy, no matter what kind, is measured in joules. All right? So it would take this amount of joules or heat energy to raise this amount of pure water from 25 degrees Celsius to 76 degrees Celsius. So where am I going with all of this theory? Well, here's a really popular type of question in the examinations. Let's say you have a water heater. A lot of people have water heaters at home. To heat up your water, you flip a switch, and when you flip the switch, a current will go through a heating element, and when the heating element gets hot, it will transfer the heat to the water, right? So here's the question. In this question, it's a kind of reverse question. We have a heater, and we put an ammeter to measure the current. The ammeter just tells us that the current in this particular circuit is 80 milliamps. This M stands for milli, and milli means you need to divide it by 1,000 first, because when I plan to use these formulas here, my current has to be in amps, not milliamps. So I'm just pointing that out one time. Obviously, the ammeter measures the amount of current, and then we put a voltmeter to measure the voltage across the heating element. So the voltage is 120, and we leave this heater on for 50 minutes, and it's trying to heat up 2,500 grams of water. Now the water, the current or the starting value of the temperature of the water is 17 degrees Celsius. Obviously, if we leave the heater on and we come back 50 minutes later, the temperature should have risen. It should have gotten hotter, right? I predict that if we leave it on for this amount of time, when I come back, it should be more than 17 degrees Celsius. So the question is, what would be the new temperature? So that's the main aim of the question. What is the new temperature after 50 minutes? Right? So it's really simple, right? Here's what. Let's put down this formula here. Let me write this back. Energy is equal to mass multiplied by specific heat capacity multiplied by the change in temperature. All we need to do is figure out how much energy is being pushed by the heater into the water. So we're trying to figure out really the energy of the heating element. And you notice for the heating element, we have things like current, voltage, and we have time. So let's see what we can do here. Well, I think we can actually use this formula. Remember, work and energy is the same thing. Work and energy, right? Some textbooks will use W and some of them will use E. So note that if I find work, I am really finding energy. So how do you find work? Work is just power multiplied by time. But the time has to be in seconds. So let's calculate the energy here. Right, so I'm going to try my best, but we're going to have to combine two formulas, because the first thing to calculate work, we need the power. We don't have the power, but it should be really easy to calculate power because we have three formulas for power. Let's try this formula here. I like this formula the most. Power is just current multiplied by voltage. The current has to be in amps. So I'm going to take the AT and divide it by 1,000. That will give me 0.08. And the voltage is good enough. The voltage is just, it's already in volts. So it's just 0.08 multiplied by 120, and this will give me a power of 9.6 watts. So we have the power of the heating element. To calculate the work or energy, we need to take the power, which we just got, and multiply by the time. So work is equal to power multiplied by time. The power is 9.6. The time has to be in seconds, so we have to take that 50 minutes and multiply by 60. Let's try that. 9.6 multiplied by 50 multiplied by 60. And we get 28800 joules. Right. So here's what we're going to do now. Let's move this. We have the work or energy. So this is the amount of energy that is being dumped into the water. So we have the energy. Let's replace. I need to erase all of this. So now we have the energy. How much is the energy? 28800 joules. We have the mass of the water. How much is the mass of the water? We have to divide this by 1,000 because the mass has to be in kilograms. So if we divide this by 1,000, we will get 2.5. The specific heat capacity of water, like I told you just now, was 4,200. And we can transpose to find the change in temperature. So, well, by the way, that's the thunder that you're hearing, so you can see I wasn't lying. 2.5 multiplied by 4,200. 2.5 multiplied by 4,200. When we multiply these two, we get 10,500 multiplied by the change in temperature. Let's throw across the multiply, and we will get a divide. And this will give us the change in temperature. So let's divide this. 28800. 28800 divided by 10,500. And the answer is roughly 2.7 degrees Celsius. This is not the end of the question, you know. They asked us what was the new temperature, and we only found the change in temperature. So if the first temperature was 17 and it changed by 2.7, then the final answer is 17 plus the 2.7. The new answer is 19.7 degrees Celsius. That's the new temperature. A lot of students would have stopped the question here, but they asked us what was the new temperature. So after we get a change, we have to add it to the 17. Because it's similar to this. Let's say I had $5 and I said that my money changed, it went upwards by $2. How much money do I have now? I have to take the $2 and add it to the 5 to get the total new amount of money that I have. Sorry. All right. So I really wanted to point out, get this question over with. Just make sure that when you're using these formulas, make sure the mass is in kilograms. Don't fall for small tricks like this. The current here is in milliamps. Make sure and convert it to normal amps. The same thing with voltage. If they give it in millivolts or kilovolts, make sure and convert it to normal volts. And time must be in seconds when you're using any of these formulas here. Once you see time, the time has to be in seconds. All right. So, see you in a few seconds with something new. All right. So, now we are going to compare series and parallel. It's a real simple exercise, and it's also very popular in the exams. Here we have two lamps. Now, just in case you didn't know the symbol for a lamp, it's just a circle with an X in it. So we have two lamps here, two similar lamps. So both of them have the same exact resistance. And we hooked these two lamps up in series to a 120 volt supply. And over here, we have a parallel configuration with the same two lamps. And of course, it's connected to the same 120 volts. Now, over here, in this question, we're going to try to figure out which of these two lamps, like these two or these two, which would glow brighter, would the series glow brighter or would the parallel glow brighter? Well, first of all, we have to figure out what would determine how bright the bulbs are. And power determines the brightness, right? So, unlucky for us, we have 3 formulas to calculate power. So at the end of the day, this is really a power calculation. And of course, now I told you before, it doesn't matter which of the 3 formulas you use to calculate the power, you will get the same answer. So let's get started with the series first. Now we're going to assume that we're really good now at calculating the series resistance and the parallel resistance. I'm not going to waste too much time doing define calculations. The golden rule for the series, we need to find the total resistance. This is in series, so to find the total resistance, we just add 5 plus 5 is 10. The total current, to get the total current, we have to take the total voltage and divide it by the total resistance. So it's just 120 divided by 10, which will give us 12 amps. So that means the current coming out of this battery is 12 amps. And remember, in series, right? The current, oh, this is parallel, sorry. In series, the current, all the resistances will have the same current. So that means the 12 amps that's flowing here, 12 amps will flow through this, come out of this, and the same 12 amps will go through that resistor. So we can calculate the power over here, and we can calculate the power over here. Now we're supposed to get the same exact answer for the power for both lamps, because both lamps have the same exact resistance and have the same exact current. So power is just current multiplied by voltage. Current is 12 and the voltage is, sorry, we don't have the voltage. Sorry, we got to use the next formula. Sorry. To calculate the power, we can use this formula because at this bulb, we have the current and we have the resistance. So let's just use this formula. Power is I squared R. The current is 12. 12 squared multiplied by the resistance, which is 5. And we will get 720 watts. Now if we do the power calculation here, it's I squared, the same current, I squared, and the same resistance. So that means it's 720 watts also. So this lamp has 720 watts and this lamp has 720 watts. Right. And remember, power determines the brightness. So let's move across to the parallel now. Let's see what's going on with the parallel. In a parallel, everybody takes a photocopy of the voltage. So you notice here is 120 volts and it's just too simple. It's just 2 bulbs in parallel. There's no series or anything like that. So that means he will take a photocopy of the voltage, which is 120 volts, and he will also take a photocopy of the voltage, which is 120 volts. Resistors in parallel have the same voltage. Now, usually the current will be different in parallel, right? But because it's 2 similar lamps, with both of them having the same resistance and the same voltage, our current would be the same. But we don't even need to calculate the current because we are already trying to find power. And to calculate power, well, for this one here, if we try to use this formula, power is I squared R, current squared by R. We don't have the current. So I'm not going to bother to use this formula, but I can use this formula. Power is voltage squared divided by resistance. We have the voltage and we have the resistance. So let's calculate the power over here. What will be the power of that lamp? Power is voltage squared, 120 squared, divided by the resistance, which is 5. And the power would get, well, I need to clear some space here. Power is 2880 watts. And of course, this one will have the same exact power because it's voltage squared, the same voltage divided by the resistance. So it's voltage squared divided by the resistance. And we'll get the same exact 2880 watts. So these two bulbs only have 120 watts each. These two bulbs, when we hook up the same two bulbs in parallel, they have a greater power. So these two bulbs will glow brighter than these two bulbs. So the main point here is parallel bulbs, provided that they are the same exact values, parallel bulbs glow brighter. But there's a disadvantage. If these two bulbs glow brighter than these two bulbs, the battery here will run down quicker. So it's a trade-off. If you want something to be brighter, don't expect the battery to last too long. But if the bulbs are dim, then you can expect the battery to last longer. It's a trade-off, right? It's almost like a rubber band. If you have a rubber band and you make it longer, you can't expect the rubber band when you stretch it to get fatter. No, when you stretch a rubber band and make it longer, the actual rubber gets thinner. It's a trade-off, okay? So I really hope this was helpful, and like I said, it's a really popular type of question in a lot of physics examinations. So see you in a little while for something else new. Hi, good day, and welcome to my first video. Well, it should only be one video on fuse calculations. All right, so let's get straight into it. What is a fuse? Firstly, I think you all should know the different symbols for a fuse. There are a couple of different symbols for a fuse. Over here, a fuse looks almost like a resistor. Remember earlier I told you all that there are a couple of symbols for resistors. You can use these squiggly lines like this, or you can use a rectangle. A fuse, though, the symbol for it is slightly different. Instead of having an empty rectangle, there's a straight line going through. So that's a slight difference between a fuse and resistor, electronic, well, the drawing for it, sorry, the symbol, sorry. And there's another symbol you can use for fuse. There's this symbol, right? Both are quite popular if you go through textbooks, but I will be using this one. So what does a fuse do? Well, too much current can damage a piece of equipment. So what a fuse does, you can think of it as a monitor. It monitors the current in a circuit, and whenever the current is too high, it cuts off the current to save the device. So inside a fuse, right, a fuse is usually, most fuses will be clear so that you can see inside of it. Is made up of glass. And inside of the fuse, there will be a wire running. Whenever the current is too high, the current will burn out the wire. And of course, with the high current, when it burns out the wire, no current can flow again. So whenever we're buying fuses or installing fuses, fuses usually come in standard sizes. I went on the internet and I researched a few sizes. Fuses usually come in 3 amps, 5 amps, 13, 15, 20, 30, and 60, and so on. Whenever you are choosing a fuse, I put a little note here, the fuse size must be just larger than the current. So we're going to see what that actually means in a little while. So here I have a circuit. Let's say this circuit represents a piece of a house where the resistances could be for things like bulbs. A bulb has a resistance. This might be the fridge, this might be the TV, this might be a microwave, all right? Just use your imagination a little bit. Just remember, everything, well, almost everything in the universe has a resistance. Doesn't matter if it's a light bulb, it doesn't matter if it's a part of the human body. All electrical devices as well have a resistance. So here's what we're going to do, right? We're going to assume, I'm just going to name these devices. Let's say this here is a fridge. Let's say this is a bulb. Over here, we have another piece of electrical equipment in the house. Let here be a TV. And let over here be a microwave. So I'll put MW for microwave. So, by the way, this is a really bad layout for electrical for a house. Like, the fridge should not be connected to the same circuit as the light bulb, but we just use it just for explaining the fuse calculation purposes. So let's do the first things first. I have a circuit, so let's follow the golden rule. Let's find the total resistance. How do you find the total resistance? Well, I think I should find the total resistance in parallel first. And when I find the total resistance of the parallel, they will all be in series afterwards. The fridge, these two items, and the microwave will be in series. So by now, you guys should be really good at finding the total resistance of circuits, but I'm still going to go through it just in case. To find the total resistance of the parallel configuration, let me just put this over here, right? Of the parallel configuration, it's 1 on 3 plus 1 on 6. The LCM is 6. You will get 2 plus 1. You will get 3 on 6. We have to flip it according to the formula, and we will get 2 amps over here. 2 ohms, sorry. So over here, the total resistance is 2 ohms. So when you squish these two resistors together, you can think of it as being one resistor of value 2 ohms. Now, 1, 2, 3. Forget these two because you squish them together to get to 2 in the first place. 1, 2, 3 are in series. How do you find the total resistance in series? Well, you simply add all of them. So, 8 plus 2 is 10. 10 plus 5 is 15. So that means the total resistance is 15 ohms. Great. Easy enough. So after we find the total resistance, you guys know by now you should find the total current. The total current is the current coming out of the battery. So, you all remember this formula? Voltage is current by resistance. If you want to find the total current coming out of the battery, you have to take the total voltage of the battery and divide it by the total resistance. So, total voltage is 240 and total resistance is 15. 240 divided by 15, guys, is how much? 240 divided by 15 is what? 240, I think is wrong, can't be so small. 240 divided by 15 is 16. All right, that's correct. The current coming out of the battery is 16 amps. So let's draw this in. Here is 16 amps. All right, so I think you know the procedure from here. The 16 amps will flow through the fridge. It will split into 2. The 16 will split into 2 and then recombine here to go through the microwave. All right, so before we install the fuses, what I would like to figure out is how much current is going through the fridge, how much current is going through the bulb, how much current is going through the TV, how much current is going through the microwave. All right, so let's see what's going on here. Well, let's calculate the voltage of the fridge and the voltage of the microwave. Remember, the fridge and the microwave, these two are the series. We're going to calculate how much voltage we have over here, calculate how much voltage we have over here, and the remaining voltage, the scraps, will be thrown to the parallel. So the total current flowing through this, the fridge here, is 16 amps. And of course, when it splits here and recombines, the current over here will also be 16 amps. So let's calculate the voltage here. Voltage is just current by resistance. So if we want to find the voltage here, we need to take the current here and multiply by the resistance here. So it's a pretty standard calculation. To get the voltage here is current multiplied by resistance, and the resistance is 5. So that means the voltage over here or across this resistor seems to be 80 volts. Now obviously if I put volts, this is voltage. I don't need to write V or voltage is equal to 80 volts. The units tells us that this here is voltage. Let's calculate the voltage over here. Current multiplied by resistance. 16 multiplied by 5. Well, over here, first of all, I made a mistake. 16 multiplied by 8. Sorry, I made a mistake. It's current by resistance. Over here, the current was 16 and the resistance was 8. So it's 128 volts. Over here, the voltage is current by resistance. 16 multiplied by 5, which is 80. Over here is the 80 volts. I apologize for that error. Right, so let's see how much voltage was pushed into the circuit. 240 volts were pushed into the circuit. He stole 128, so I'm going to minus 128 from the 240. And I'm also going to minus the 80 from that 240, which is going to leave us with 32 volts. That's the scrap volts. So we are going to throw that into the parallel configuration. Well, over here, everybody will take a photocopy of the voltage. So if the remaining voltage is 32, he will take a photocopy, so he's 32 volts, and the voltage across the bulb is also 32 volts. So now we can calculate the current through each of these devices. Now let's see if we can predict the answers. Over here is the smaller resistance, and over here is the larger resistance. The smaller resistance is supposed to get the larger portion of the current, and the larger resistance, the 6, is supposed to get the smaller portion of the current. So how do we calculate current? Current is voltage divided by resistance. So let's start here. Current is voltage divided by resistance, which is 6. And over here, we get 5.3 amps. The current over here is the voltage, which is 32, divided by the resistance, which is 3. And over here is 10 point, well, if you round it off properly, it's 10.7 amps. And look at it, our answer once again makes sense. The current by the smaller resistance is higher than the current with the larger resistance. All right, so now time to install our fuses. Let's say we wanted to protect the TV. How much current is flowing through the TV? Well, approximately 5.3 amps. So when we are installing a fuse here, the fuse size must just be larger than the current, not too much larger. So let's see, this here is the current. Can we install a 5 amps fuse? No, 5 amps. This fuse size will be smaller than 5.3. We have to choose something bigger on the list. So we cannot choose a 5. So if the next available size of resistor is 13, we have no choice but to install a 13. We cannot install something smaller. So if I am installing a fuse here, I'm going to install my little fuse there. That's a symbol for a fuse. I'm going to put a 13 amp fuse here. Right? If I had to install a fuse to protect this light bulb, the current flowing through that light bulb is 10.7. Can I install a 5? No, 5 is too small. But I can install a 13 because 13 is just larger on this list than the 10.7. So I'm guessing I could protect this with a 13 amps fuse. If I wanted to protect the fridge is 16 amps. I cannot put a 5, that's smaller than 16. I cannot put a 13, that's smaller than 16. I cannot even put a 15. 13 is still smaller than 16. What's the next size available? It's 20. So I have to install a 20 amps fuse here. And this one is also 16 amps. So if I needed to protect the microwave, well, I need to install 16 amps as well. Right? Now, the fuse calculations are really simple. This is like a really difficult question by exam standards. Just remember, a fuse size must be just larger than the current. The current I'm talking about is the current flowing through that particular device. Okay, guys? Now the thing about a fuse, if over here this is a 20 amps fuse, let's just say, and there's a lightning strike and there's a surge. Let's say that the lightning causes the current to go up to 24 amps. This is a 20 amps fuse. If you try to push 24 amps through this, the wire will burn out. And that's a good thing, because when the wire burns out, the 24 amps, which caused the wire to burn in the first place, cannot flow through the fridge. The 24 amps would have damaged the fridge. But because of the fuse and its 20 amp rating, it protected the fridge. Now the thing about a fuse, once the wire burns out, you need to replace the fuse. You have to go to the electronics store and buy a brand new fuse. So fuses are like, once it does its job, you discard of it and you replace it with a new one. And that's a kind of disadvantage of a fuse. It's not reusable once it has served its purpose. But fuses are pretty cheap in most instances, so it's a trade-off. One use, but it's cheap. Another device that you can use to protect your fridge or bulbs or TVs or whatever, instead of using a fuse, there's something called a circuit breaker, which I will make a separate video on, but it's going to give you a brief introduction to it. A circuit breaker is something, it serves actually the same function of a fuse. It protects a device whenever the current is too high, because high currents tend to damage pieces of equipment. But the thing about a circuit breaker, it's reusable. A fuse is not reusable. Whenever a circuit breaker stops a high current from flowing, you do not need to go and buy back a new circuit breaker. You can reset the circuit breaker to be used again. But I'm sure you already guessed that a circuit breaker is a little more expensive than a fuse. But like I said, I'm going to make a separate video soon showing you the complete differences between a fuse and a circuit breaker. Until then, guys, take care. Hi, and welcome to my video on, dry cells, which will also lead up to something called primary cells and secondary cells. So, first things first, what is a dry cell? I'm pretty sure that everybody here has seen a dry cell, but you may not know the scientific name. This here is a dry cell. Alright? It's just basically what you normally call a battery, a portable battery, which comes in size like double A or triple A batteries. Alright? So, here I have a dry cell, and today we are going to be labeling the different parts of a dry cell. Like if we were to take this battery and to cut it open, what would we find inside of it? Alright, now first things first, I would like you all to pause the video and draw this diagram for the time being. Right, so I'm going to assume that you paused it and drew it and you just came back. So there are some parts I'm not really going to discuss in detail because it's super easy. That's like the cap, the cell cover, and the protective case. Those things should be pretty obvious in a dry cell. Well, on top of the cell here, you'll see a little nose. I'm sure you have seen the little nose. That's the cap. Underneath the nose, there's a flat plate, that's just the cell cover, like to keep everything in. And around it, you can see a protective casing. So those things are pretty easy to recognize because they are on the outside of the dry cell. But if we were to cut it, we will find a number of things. First of all, underneath the cap, there's a carbon rod, which is this rectangle here. That's your carbon rod, and your carbon rod will usually have a positive charge. Over here, and you see this part here where it's shaded kind of bluish? That part is your ammonium chloride paste. Underneath, but further inside the cell, this yellow part here, that's a mixture of manganese dioxide and powdered carbon. And surrounding the ammonium chloride, the manganese dioxide and powdered carbon, and the actual carbon rod, this U here, right? That's your zinc casing. So in the exam, the examiner can ask you to draw the dry cell, and he can ask you to label the different parts of the dry cell. So sometimes you need to call things by their technical names. The ammonium chloride paste is usually called your electrolyte. So over here, this is your electrolyte. What happens is that the ammonium chloride, this chemical, will react with the zinc casing. So these two will react, and when they react, they produce a current. Now, how does the current flow? Now, there's two types of current, well, two names basically. There's one called actual current flow or conventional current flow. When the ammonium chloride reacts with the zinc casing, let's say you take a piece of wire and put it at the base of the dry cell, and you run this wire all the way to the top. Now, obviously, the cap is connected to the carbon rod. Electrons will begin to flow from the zinc casing all the way in this direction towards the carbon rod. Now, this is actual current flow, but if they ask you for conventional current flow, conventional current, actual current, the flow of electrons, remember the zinc casing has a negative charge, actual current flows from negative to positive. Remember the carbon rod has a positive charge. But conventional current assumes that the current flows from positive all the way to negative. So if the examiner were to ask me which direction is the current flow, and he didn't actually specify if he's talking about conventional current or actual current, I would take that opportunity to distinguish between the two. I would just simply say actual current flow, the flow of electrons, flows from the zinc casing, which is negative, all the way to the carbon rod, which is positive. And also, conventional current flows from positive, the carbon rod, all the way to the zinc casing, which is negative. I'm not going to leave any holes in my explanation, right? In case the examiner forgot to specify whether it's actual or conventional current. All right, so moving on. The zinc casing is negative. Your zinc casing is regarded as your anode, right? That's the type of, oh God, I forgot the name of it. That's the type of electrode over here. And the carbon rod is considered to be your cathode. So sometimes you go on the internet and you search for diagrams of the dry cell. Instead of calling it the carbon rod, they call it the cathode. And instead of calling it the zinc casing, they call it the anode. So actual current flow actually flows from the anode all the way to the cathode, and conventional current flow flows from the cathode all the way to the anode. All right, so they might also ask you what's the different functions of all of these parts. Well, the main functions are, it is not all the parts. The protective casing is just to hold everything together and protect the actual battery. I'm not going to go through simple things like that. If they ask you what's the purpose of the ammonium chloride, the electrolyte, and zinc react to produce electricity. That is what you want to write. So write this down in your books right now and memorize it. If they ask you what's the purpose of the manganese dioxide and powdered carbon, well, it's really simple. The manganese dioxide removes the hydrogen gas created during the reaction. To keep it simple, remember, this is not chemistry, although there's a little bit of chemistry in physics, I would agree with that. When the ammonium reacts with the zinc casing, right, with the zinc actually, hydrogen is produced. And what you want to do is get rid of that hydrogen. You don't have to know why for CXC or CSEC or O-level physics. You just need to know that hydrogen is produced. And the purpose of the manganese dioxide is to remove the hydrogen gas created during the reaction. Write that and you will get your marks. Alright, and I think I already covered this one. This is the current flow. Current flows from the negative terminal, the zinc, all the way to the positive. Alright, so they will most likely ask you what's the function of the ammonium chloride paste. Well, the ammonium chloride paste works with the zinc and the purpose of the manganese dioxide. Alright, so what you need to know now that the dry cell is something called a primary cell. Right, so I'm going to put this here. There are main two types of batteries or cells. There's a slight difference between a cell and a battery. A cell is singular. A battery is a combination of cells. Okay, so let's not get into that right now. There are two main types of batteries. I'm sure you're very familiar. Some batteries are rechargeable, like for your cell phones and whatnot. You can recharge your battery. But some batteries, like the one I'm holding in my hand right now, once we're finished using it, it cannot be used, it cannot be recharged. So these are not rechargeable. So the two main categories of cells are primary cells and secondary cells. This here is an example of a primary cell, which a lot of you are very familiar with, especially the older folks who grew up with these types of batteries. They probably didn't have much rechargeable batteries for people growing up in the 80s or 90s. They were around, but probably not affordable to a lot of people. Right, so a primary cell, which are these, if discharged, which basically means if you're finished using it, it cannot be recharged. I'm sure you're very familiar with that. They're usually very light in weight. They don't provide very high current. It's usually a low current these things produced. Because if I touch these two things here, I'm not going to get shocked. They also have something called a high internal resistance. Remember, everything has a resistance. This marker has a resistance. My hand has a resistance. So this battery and all its components also have a resistance inside of it. That internal resistance, the resistance inside of this, is usually high, 5 to 8 ohms. And of course, primary cells are also cheap. Please memorize this and take this down in your books. A secondary cell is a rechargeable battery. If discharged, that means if you're finished using it, it can be recharged, right? It's a rechargeable battery. They're usually heavy in weight. That's the opposite of a primary cell. And they're capable of high current, unlike a primary cell. And inside of them, the components, they usually have a low internal resistance, less than 0.05 ohms usually. And I'm pretty sure that you're well aware that secondary or rechargeable batteries are more expensive than primary cells. All right, so please just don't watch this video. Make sure you take down all the notes. These are standard questions that come in exams, especially this chart. They can write this table, put in a few, and you will have to fill in the blanks. All right, guys, so I'm not going to make this video long. It's very straightforward. You just need to copy it down and learn it. All right, guys, don't forget to subscribe to my channel. Take care. All right, so Welcome to my next video, and today we are going to be discussing ammeters and voltmeters. This is going to be a really short video because the syllabus doesn't require too much about ammeters and voltmeters, right? Compared to what you need to know in CAPE or university or whatnot. So 5 minutes tops. Okay, so an ammeter is used to measure current. A voltmeter is used to measure voltage. Ammeters must have a low resistance, but voltmeters, even though it's hooked up in parallel, it needs to have a high resistance. So pause the video, take down that note. Alright, so the whole idea of when you're inserting an ammeter in a circuit, it needs to appear invisible. The circuit should not know the ammeter is over there. The ammeter should call minimum disturbance in the circuit. Same thing for a voltmeter. When you're putting in, or when you're installing or inserting, a voltmeter in a circuit, it should appear invisible to the circuit. I often make the analogy that, let's say you're trying to observe someone's natural behavior. You're really trying to figure out how they behave, behave naturally. Sorry for the mix-up here. So if you tell that person that you are going to observe them and their behavior, that person will never behave as they really do, because they know someone is watching them and monitoring them and making notes on them. So for you to get an idea of how that person really behaves, they must not know to any extent that you are observing them. Does that make sense? Same thing with a circuit. When I put in the ammeter, the circuit should not know it's there. When I put in the voltmeter to measure the voltage, it should not know it's there. And what that really boils down to is that if you're trying to measure the current or the current or voltage through this particular resistor, it should not affect the current flowing through it. So an ammeter has a low resistance, or it should. So if I were to insert an ammeter inside here, right? Let's say I insert an ammeter here. If this ammeter has a very high resistance, so let's say it has a very high resistance. Let me bring back an old chart for you here. You remember, when something has a low resistance, plenty current will pass through it. If something has a high resistance, a small amount of current will flow through it. So if I insert, let's say that the current without this ammeter is, let's say it's 8 amps. When I insert an ammeter with a really high resistance, a high resistance will reduce the entire current, and the entire current of the circuit might drop to something like 3 amps. But the actual value is supposed to be 8 amps. So for this ammeter not to affect the circuit, it must have what instead? A low resistance. A low resistance might bring up back the value, not to 8, but at least to something like 7.99. Everything has a resistance. It's practically impossible to get an ammeter with 0 resistance. But you want the resistance to be so low, it doesn't affect the actual current flow through the resistor. So how do you put that in words to the examiner? Well, if they ask you, well, how should an ammeter be placed in a circuit and why? This would be my explanation. So pause the video and take down this explanation. An ammeter is placed in series with the circuit element of interest. That's this guy here. And it measures the current through the element. Remember, he's trying to measure the current through the element with minimal change in that current. When you insert that ammeter, you don't want it to drop the current to 3. You want to keep it at 8. 7.99, due to the low resistance, is not that far from the 8 amps. So that should allow you to get full marks in the exam if asked that question. Let's try the voltmeter now. Let's finish with this guy here. Let's close back up this circuit. Right. So a voltmeter should be placed in parallel to the item, not in series, and it should have a high resistance. Now let's put high R. All right. The reason for having a high resistance is that, let's say 8 amps is flowing through here. Remember, you want the full 8 amps to flow through the 5 ohms. You don't want any of the amps to be stolen by the voltmeter, because if some of the amps go above the circuit, it would affect the current flowing through the 5 ohms. And of course, you can think of it like this. Once the 5 ohms realize, wait now, I am not getting my full 8 amps. Somebody is stealing some of my amps. The voltmeter will not be invisible to the circuit. The resistor will figure out that, hey, somebody is stealing my current, and go and look for the voltmeter. Remember, the whole purpose of the ammeter and voltmeter, it needs to appear invisible to the circuit. So if here has, let's say it's a really bad voltmeter and it has a low resistance, well, when the current reaches this junction, remember, current likes low resistance, so a lot of the current will flow upwards. Let's say 5 amps flows upwards. That only leaves 3 amps to flow here. The full 8 amps will not make it through the 5 ohms. So that's why it's imperative that it must have a high resistance. If here has a really high resistance, like let's say it's 1,000,000 ohms, then even though this has a high resistance, it's impossible to get a voltmeter with an infinite resistance. But if the resistance is super high, only a small amount of current will flow through this voltmeter. So that means if 0.00001 amps flow through this voltmeter because of the high resistance, that leaves how much to flow through the actual resistor? 8 minus 0.00001 amps. That leaves 7.99999 amps to flow through this resistor. This 5 ohms, unless he's really particular and really vigilant, he is not going to notice this amount of current is missing. He got basically 7.99999 of the amps. So the voltmeter virtually remains invisible to the circuit. So how do you put that in words for the examiner? Well, a voltmeter is connected in parallel. That's true, must be in parallel, right? To measure the change across a circuit element. Its resistance is very high, right? It must be high. So it diverts a minimal amount of current away from the intended path. Remember, some of the current will be diverted through the voltmeter, but you want that value to be as small or minimal as possible. So the majority will flow through the actual element of interest, the element of interest being the 5 ohms. Alright, so pause the video, take this down and memorize it. So guys, I really hope that was helpful. Stay tuned for my next video on electricity. Alright, today we will be looking at current voltage relationships. Okay, so the symbol for current is I and the symbol for voltage is V. Now there are many different types of components on the syllabus. I'm going to try to cover the most popular here. I'm sure everyone knows what a filament lamp is. It's just a lamp. There's something called a thermistor and something called a semiconductor diode. Now, whenever you alter the voltage through an electronic component, the current will also change. But the current doesn't always change the same way as the voltage is changing. So the first thing I need to do is introduce to you something called an ohmic conductor. An ohmic conductor, you can think of it as the world's most perfect conductor. And here we have a y-axis representing the current and an x-axis representing the voltage. Now, this here is the positive y-axis and the positive x-axis. Behind here is the negative x-axis and the negative y-axis. Don't let the negative axes get to you. Sometimes current can flow forward and sometimes current can flow backwards. Everything on the positive is assuming that the current is flowing one direction, and everything on the negative axis are just assuming that the current is flowing the opposite direction. But don't let it get to you, okay? So what is an ohmic conductor? If we were to take an ohmic conductor, which to the best of my knowledge doesn't exist, right? It's like the ideal conductor. Whenever you plot the graph, like if you were to change the voltage and alter the current and plot a graph for that, you would get a perfect straight line. The line would go on forever and ever and ever and ever, but it would be perfectly straight. So, let me bring some maths into this. By now, you should have encountered this formula. Gradient is y2 minus y1 divided by x2 minus x1. So what is the gradient? Gradient is just another word for steepness, or how steep the line is. Now, in an ohmic conductor and any straight line, the gradient at any point on the line is the same. So if the gradient here is 4, the gradient here is also 4, the gradient at this point is 4, and the gradient at that point is 4. But let's investigate the gradient formula a little more. The gradient formula, on top you have the y values, you can clearly see it here, the y values, and you are dividing it by the x values. So in other words, the y values go on top and the x values go at the bottom or underneath. Great. Now, let's investigate the formula for resistance. I'm very sure you have seen this already, had it at the beginning of the video. Resistance, if you block the R, is voltage divided by current. So, resistance is just voltage divided by current. But look at the graph, right? On the y-axis, you have current. On the x-axis, you have voltage. So, my voltage, according to all of these graphs, go on the x-axis. And all my current values go on the y-axis. Okay? So, this is just the opposite of the gradient formula. In the gradient formula, the y's go on top and the x's go underneath. So, in an ohmic conductor, right? If I had asked you to find the resistance of the component the current is flowing through, you would have to find the gradient of the line. So you would take 2 points on the line. You call one point x1 and y1, and the other point x2 and what? y2. But when you find the gradient of the line, remember, resistance is the opposite of the gradient formula. So let's say that you found the gradient of this line. So let's the symbol for gradient is m. Let's say the gradient was 2. And I asked you, what was the resistance of the component? A lot of persons would have said the resistance was 2 ohms, but that would be wrong, because resistance is the opposite of this. If you take this and flip it, you will get the formula for resistance. So the actual resistance of the component, where 2 is the same thing as 2 on 1. So if you flip that, you will get a half. The resistance, and remember, the resistance of the component is a half. And at any point on this line, the gradient is 2, which means that at any point on this line, the resistance is also a half. The point I am making is that in an ohmic conductor, the resistance remains the same for the entire graph. And the next point I want you to make a note of, the resistance is the inverse or opposite of the gradient. So whatever you get for the gradient of the line, you need to flip it. Right? That's an ohmic conductor, which is the world's most perfect conductor, which to the best of my knowledge doesn't really exist. All right, let's try a filament lamp. A filament lamp has a resistance. A filament lamp is not perfect like an ohmic conductor. In fact, it's not an ohmic conductor. It's not ohmic. But before I actually draw the graph for the filament lamp, right, let's investigate two lines here. I have a black line curving upwards like this, and I have a green line. Now, finding the gradient of a straight line is really, really easy. You just have to take 2 points and throw it into that formula. But a curve is a little bit different. To find the gradient of a curve, what you need to do is draw a tangent. A tangent is like a straight line that just grazes the curve at one point. So let's investigate what is happening with the curve from A to B. Let's investigate what's happening to the gradient. If I wanted to find the gradient at this point here, I would have to draw a tangent. Right. So the tangent would just scrape the curve at that point. If I wanted to find the gradient here, I would have to draw a tangent here. And if I wanted to find the gradient here, I would have to draw a tangent at that point. Now let's investigate what's happening from A to B. Let me just write back B properly here. Look at the tangents. Is the steepness of the tangents increasing or decreasing? Look how steep this line is. Look how almost flat this line is. So as we go from A to B, your gradient decreases. Right? So as you go from A to B, the gradient or steepness gets less and less and less. Pretend this was a hill. It starts off really hard to climb. But as you go higher and higher, you notice it gets flatter and flatter. So, I spelled gradient wrong here, sorry. So if the gradient increases, remember, gradient and resistance are opposites. The formula is flipped. Here, y is on top, x is underneath, but over here, x is on top and y is underneath. So if the gradient increases, that means from A to B, the resistance increases. Right? So the gradient decreases, but from A to B, the opposite happens for resistance. Resistance increases. Right? Note the shape of this, and you'll be seeing this soon. All right. So let's see what happens when the curve goes the other way. If you start off at A and you draw a tangent at each point, you will notice that the lines are getting steeper and steeper and steeper. So the gradient increases. So that means since gradient and resistance are opposites, as you go this way, the resistance decreases. So let me draw the shape, the shape of the curve for a filament lamp. A filament lamp looks like this. All right. As the voltage increases, you notice what the curve is no longer. It's straight for a little bit, and then it starts to curve this way. This curve, it's like this curve. So what happens to the resistance as we go this way? The resistance increases because the gradient decreases. So as we go this way, the resistance increases. And as we go backwards, the same thing basically happens. The resistance increases as we go this way. So remember that the shape for the filament lamp. A thermistor is the opposite. Instead of curving, like getting flatter and flatter, it goes like this. It starts off straight and then goes upwards. Starts off straight and then gets. You notice this one is getting more and more steep, and this one is getting more and more steep as you go backwards. So that means it's taking the shape of this curve. So as the voltage increases, resistance, as you go this way or this way, resistance decreases. All right? So that's really, really, really important to note. The diode is the odd one out. This is the shape of a diode, the current, the voltage current relationships. It's flat basically for a while and then it shoots up like this. And if the current tries to go backwards, to be really accurate, there's just a small current when the voltage is reversed. All right, the semiconductor diode is the easiest to spot in the exam. I haven't discussed semiconductor diodes in detail, but I'm going to give you the symbol for a diode. This here is the symbol for a diode. And what a diode does, it only allows current to flow in one direction. So for example, if in a circuit, you had current going this way, and then the current was reversing, and you didn't like the fact that the current was going two ways, you just insert a diode, and a diode is like a police officer in the circuit. He will say, hey, current cannot flow both ways, go this way only. Anybody who is going the other way will be stopped and given a ticket. So a diode allows current only to flow in one particular direction. If the diode is facing this way, if the line is on this side of the tip, current is allowed to flow that way. If the diode is facing this way, you notice the line and it's touching the tip of the triangle, that means current is only allowed to flow the opposite way. If any current tries to flow this way, it will be stopped. Any current trying to flow this way will be stopped. Alright guys, so I hope this was helpful. Pause the video and take down all of this. Memorize the shapes of these graphs here. Alright, so next I'm going to be discussing alternating current and direct current, and I'm going to discuss the diode as much as the syllabus requires. Alright, so welcome to the next part of this video on the two types of currents. Now, the two types of currents that you're going to bounce up on the syllabus is AC and DC, alternating current and direct current. To make it simple, alternating current, the current flows in two directions. So sometimes the current is going this way in the circuit and sometimes the current is going the other way. It's alternating its direction. Direct current, the current only flows one direction. So I'm going to represent AC and DC on graphs. It's going to be very, very simple. Now, here we have a y-axis and here we have the x-axis. The x-axis is time and the y-axis is current or voltage. Now, when I say current or voltage, remember from my first video, I told you voltage is the force that pushes the electrons to get the current. So, if you have an alternating current, it's obviously being caused by an alternating voltage. And if you have a direct current, the current that is flowing in one direction, then the voltage is obviously pushing only in one direction. All right? So don't get too confused if the y-axis is current or voltage. That isn't going to be too important right now. So let's do the DC first. That's the easy one. To represent a DC on graph, you have to make sure that the graph is only on one side of the x-axis. For example, this here is a DC current because notice it doesn't cross over into the underneath of the x-axis. Also, this here is a DC current. Because it's above the x-axis, it doesn't cross over. Similarly, if I have it underneath, once it doesn't cross over, if it starts off underneath, it cannot cross the x-axis and go on the other side. So these here are three examples of a direct current. And in this case here, the current is only flowing one direction. So this here is DC. AC, on the other hand, Sometimes the graph is above the x-axis and sometimes the graph is below. So this here is an example of an AC current. Piece must be above and piece must be below. Pretty simple. I'm not going to go too much into detail again regarding crossing over the x-axis or going below the x-axis. What I want to do is discuss something called the diode now. Remember in my previous part of the video, I explained that a diode is something that only allows current to flow in one direction. Alright, so let me erase this DC here. I'm only interested in the blue one right now. So let's say I have a DC supply. Now, in case you didn't know, a battery or a cell, a normal car battery provides a DC current. And conventional current always flows from the positive all the way around to the negative. Okay? So, let's assume that this is a resistor and we have a DC supply, a battery, and this is how the current looks through this resistor. Let's assume the value of the current is 5. If I were to put a diode here, so I cut the circuit and insert a diode. The diode allows current to flow from the back of the triangle to the front of the triangle. So, this police officer or diode allows current to flow this way. So, this will not affect the circuit because the current is attempting to go from here in the correct direction through the diode to the negative. So, the graph looks like this. However, if I were to reverse the diode like this, current can only flow this direction, but all the current from the battery is flowing the opposite direction. So what will happen in a case like this? No current will flow and it will be level with the x-axis. With the x-axis. So I'm trying to draw it, but it's going to be 0. So that's how a diode would behave in this particular circuit if we were to reverse its direction. This one here, an AC supply, this here is the symbol for an AC. Sometimes the current tries to flow this direction, and then, since it's an AC supply, the current will reverse directions. So sometimes, in this case here, the above, I'm going to color code it for you. Anything above the x-axis represents current flowing this way. But every once in a while, after a certain amount of time, after the current flows this way, an AC supply will reverse it. And I'm going to put that in green. And then it would make it go the other way again. So we get the blue. And then it would reverse the current, so we'll get the green. So the blue represents current flow in this direction, and the green represents current in the other direction. So what would happen if we were to put a diode? Well, if we were to put a diode facing this direction, that means it will only allow current to flow that way, which is the direction of the blue part. So that means when the current reverses direction, that's the green arrow, it will not be allowed to flow. So all the blue will be allowed to flow, but all the green will be discontinued. So there will be current, and then for a brief moment in time, there will be no current because the diode is preventing the current from flowing the opposite way. You notice that half the graph is gone, only the top part is staying, and only the underneath part is staying. You notice this is actually a type of DC. When we insert the diode, nothing goes below the x-axis, making it a DC. You call this scenario half-wave rectification. Half-wave rectification throws away half of the graph, in this case here the underneath of the graph, and only leaves you with the other half. And this is actually DC now. So this is how you can actually convert an AC. Now it was an AC just now because it had the underneath part as well as the top part. But when we put the diode, we threw away the underneath part and we were left with only the part above the x-axis, making it a DC supply. It isn't a great DC supply because that means you would have current, and then for a brief period, there would be no current. Then it would have current, and then no current. So it's a DC, but not a very good DC. All right, guys, so I really hope that you understood this. And I think this would be the last part of the video regarding electricity. In my next, well, look out for my next series of videos, and that's going to be on electromagnetism. We're going to mix electricity with magnetism. All right, so take care. Have a good day, guys.